let's take a look at the idea of calculating curvature. Now, a parameterized vector r of t is called smooth on an interval I if r prime, the first derivative of the vector function, is continuous on I. This is an I, not an L. And r prime of t is not equal to the zero vector on that interval I. Now, a curve is called smooth if it has smooth parameterization. In other words, a smooth curve does not have cusps. So a curve that looks perhaps like this is an issue. Right there's a cusp. So this is not smooth. Whereas something that just looks like this, there are no cusps. This is a smooth curve. Now, let's let C be a smooth curve defined by the vector function r of t. The unit tangent vector is then given by, and we're going to use a capital T of t, and this is a vector, equals r prime of t divided by the magnitude of r prime of t. Well, which kind of makes sense. I mean, r prime of t is going to be the tangent vector. So if I turn this into a unit vector, which I do by dividing by the magnitude, it becomes a unit tangent vector. But we very commonly use this capital T to represent it because it's kind of a special vector. We will see it a lot. Other notations you may see, maybe t hat, the little hat there, is sometimes used to represent a unit vector. So this would be the unit tangent vector. The unit tangent vector indicates the direction of the curve. Now then, the curvature that's an R, curvature of C at a point, or at a given point, is a measurement of how quickly the curve is actually changing directions at that specific point. So, if we think of S of t as being the integral from 0 to t of the magnitude of r prime of u du. This is what we did when we parameterized the arc length. So if this is the arc length as a function of t, then ds dt, the derivative of this guy with respect to t, is equal to the magnitude of, well, that's actually going to be t now, r prime of t. Obviously, this is a vector function, just like this is the vector function. Now, this is actually pretty important because, keep this in mind, we're going to need this in just a moment. Curvature is defined as a rate of change of the unit tangent vector with respect to the arc length. Or another way of saying this, and we typically use the Greek letter kappa to represent curvature, kappa equals the magnitude of, dt ds, the derivative of the unit tangent vector with respect to arc length. That's what this is, the arc length, which by the chain rule we can simply write as dt the derivative of the unit tangent vector with respect to t equals dt ds dt. Therefore, dt ds equals, let's see, dt, I know that sounds funny in English, but you can see the capital in a smaller letter, so you actually know what I'm talking about, over ds dt. Well, the derivative of the unit tangent vector with respect to t, that is simply t prime of t over what ds dt, we just got done saying, is the same as r prime of t. Therefore, kappa, the curvature, is equal to the magnitude of t prime of t over the magnitude of r prime of t. So this gives us a way that we can actually find the curvature at a specific value of t.